All right. Hello, class. Mr. Pettibone here with another lesson for you guys. Um, I wanted to start off with a bit of a news announcement. Um, so, let's see. I want to remind you that we're doing 4 days a week now, so we'll have no lesson tomorrow. Today's lesson is going to be qualitative in nature. There's not really any equations to practice or anything, so there's going to be no daily item for today. And let's see. Next week is the last week for seniors, and because the class is, something like 40% seniors, I'm just going to stop the class next week. So there's going to be no final exam. There will be one more quiz on astrophysics that I'll assign at the beginning of next week, but that's it. So and I think the week after next, I'm supposed to continue teaching for juniors and sophomores, but I think we'll probably just have maybe we'll have a Zoom meeting and we can all just hang out for half an hour or something, and that'll be our final class for the juniors and sophomores. So I won't tell if you guys won't tell. We're just going to stop it next week for everybody. Let's see who's watching. We got Zena. Hi Zena. Hi Ava. Hey Kyle. So what I want to talk about today is stars, stellar physics. So today we're going to talk about the physics of stars. Okay. Hey Goldie, hey Rourke, hey Sebastian. So, what is a star made up out of? Stars are made up out of mostly hydrogen, some helium, and trace amounts of other stuff. Okay. And so in the center of a star, which is called the core, is doing, so it has, now one of the things about stars is that they, at the center, they have incredible pressure, incredible temperature. So the surface of the sun, for example, is about 5,000 Kelvin, but the interior is significantly hotter than that. If I remember correctly, it's like millions of Kelvin or tens of millions of Kelvin. So so the center of the star is incredibly hot, incredibly high pressure, and those are conditions where nuclear fusion can occur. Okay, and nuclear fusion releases a lot of heat. You're basically taking the potential energy of an atomic nucleus and you're turning it into thermal energy. Okay, so it's a giant thermonuclear explosion happening in the core of a star. Okay, and what I want you to realize is that the size of a star is determined by a balance between explosive force and gravity. Okay, so those two are in equilibrium with each other. You've got the interior of the star is trying to blast it apart, and gravity is trying to pull it together. And so the size of the star that we see is determined by the balance between those two. And so if that balance changes, the size of the star will change. So for example, if the interior of the star became less explosive, then gravity gets the upper hand and the star will shrink. Now, of course, if the star shrinks, the interior gets hotter and you get more fusion, which will halt the contraction of the star. If the star becomes more explosive in its core, then the outside of the star gets bigger. So it's a balancing act between these two. You could think about the sun as a continual explosion that's being contained by gravity. If we were to flip off gravity and have no gravity, then the explosion would win and the star would just get bigger and bigger and bigger. But of course, as it gets bigger, the density of the core is reduced, and so you have less fusion happening. So the star would burn itself out if gravity were turned off. So the stuff around a star is the stellar system. So what, and I'm saying stellar system, when I say a solar system, I mean our sun. But, all stars have stuff that are orbiting them. And, if it's a young star, then there's a lot of gas and dust that's orbiting the star. But as time goes on, that gas and dust, it tends to coalesce into, so it could be gas, dust, but later on that gas and dust coalesces into other objects, which are planets, asteroids, comets, etc. So, and then, so all the gas and dust that was initially in the solar system has all fallen onto planets, asteroids, comets, etc. Okay. Interesting fact, most stellar systems have two stars. That's actually more common than one star. Okay, so it's called a binary system. In fact, hello Andrew and Jin K. In fact, the closest star system to us, which is called the Centauri System, has 3 stars in it. So if a system has 3, so 2 stars, it's something like 2 stars sort of dancing around each other like this. If you have 3 stars, what it tends to look like is like 2 stars, a binary system, but then there might be a third star that's going around both of them. Okay? And then if you have 4 star systems are not common, because if you have 4 stars, what tends to happen is one of the stars will get pulled super close to another one, and then it will get ejected. So you basically, that 4th star will tend to get a lot of kinetic energy through its gravitational interactions with the other 3 stars, and it'll get flung out of the system. Okay? And then it'll just be a solo star. That can happen with 3 stars too. So that's, so yeah. So let's talk about the life of a star. Okay. Let's talk about the life of a star. So what happens is you start out with, a cloud of gas, which is, in astronomy speak, we call a cloud of gas a nebula. And something causes that cloud of gas to start to contract. So gravity causes it to contract. Now, as it contracts, you have the volume of the cloud shrinks, the pressure goes up, and the temperature goes up. And so eventually the center of the cloud gets hot enough that you have nuclear fusion occurs. And so when that happens, you have what's called a protostar. So that's just a really young star that is, so in order to be considered a star, it has to have that fusion happening. And so the protostar, it's not really well defined. It doesn't have a well defined boundary like the sun does, for example. You look at the sun and it's like there's obviously sun and then no sun. So a protostar hasn't really absorbed all of the, so I'm going to use a technical term. We say accrete. Accrete is the astronomy term for, due to gravity, it gobbles up matter. Okay, so protostars have not accreted all of the mass in the system yet, and the planets haven't accreted all of the mass. So there's a lot of gas and dust in the system still. But eventually that happens, and the star enters its main sequence. So the main sequence is where the star spends most of its life. And during the main sequence, the core of the star is converting hydrogen to helium. Okay? Through fusion. So you're taking hydrogen nuclei and squishing them together to make helium nuclei. All right? And so the sun, for example, is on its main sequence. Then, once we go past the main sequence, we start to enter what's called the giant phase. Okay? And what triggers the entrance into the giant phase? Basically what happens is, as the core of the star is aging, we're getting more and more helium built up in the core of the star. And once the core of the star has too much helium, then we're no longer fusing hydrogen in the core anymore, and we start fusing helium. So we start fusing helium into other stuff, and there's a whole chain of things that the star can fuse. It can go, I believe it fuses helium into carbon, and then it fuses carbon into other stuff, and blah, 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 blah. And so the thing is that when a star starts fusing helium, helium is more explosive. More energy is released by fusing helium than is released by fusing hydrogen. And so the star gets more explosive. And so as a result, again, the size of a star is determined by the balance between explosion and gravity. And so it gets more explosive, and so the size of the star gets bigger. Okay? In fact, when the sun enters its giant phase, its radius will be approximately 1 AU, meaning that the Earth will be swallowed up by the sun. Now, even though the interior of the star is more explosive and hotter than it has ever been before, the outside of the star has been puffed out so much that the outside is actually cooler. And so the color of the star changes to the color red. So it's called a red giant. Okay? Yeah. And so a couple of things can happen. Now, I should say that it can actually sort of go between the giant phase and the main sequence and go back and forth. So it can actually change its size several times. Red giants are brighter than main sequence stars. Why is that? Well, even though they're cooler, so the surface of the star, the brightness per surface area of the star is less. The star gets so much bigger that it's a lot brighter. So the fact that the surface of the star is less bright is compensated by the fact that there's a lot more surface of the star, so it gets brighter. Now, if the star is low mass, the sun is not a particularly high mass star, then it's going to turn into what's called a white dwarf. So what happens with the white dwarf is basically the star has fused everything that it can fuse, and it can't fuse anymore. And so basically the amount of explosion goes to zero, and so gravity takes over again and compresses the star back down, and it becomes a white dwarf. So white dwarfs are incredibly hot. They're roughly the size of the Earth. So they're very dense because, now why are they so dense? It's because there's no more fusion happening in the core. It doesn't have the right composition in terms of elements to have fusion anymore. You can't just fuse anything. So it just shrinks down. Extremely dense. But so there's no more fusion happening in the center. But it's not enough mass to collapse into a black hole. Okay? All right? So you still have individual protons and electrons. But if we have a higher mass star, and I can't remember what the exact boundary is. I want to say it's something like 10 solar masses or 8 solar masses. Then the star has what's called a supernova. And a supernova is a gigantic explosion. So what happens in a supernova? Well, a star fuses hydrogen into helium. It fuses helium into carbon. It fuses carbon into heavier stuff. And eventually we get to iron. And it turns out that iron is sort of the last element that can be fused. Okay? If we go to elements beyond iron, star doesn't want to fuse anymore. It wants to actually have fission, where the nuclei split apart. So iron is the last element that can be fused in the core of a star in any significant amount. And so what happens is the core becomes basically made out of iron, and no more fusion can occur. So the fusion gets shut off. And this happens in a matter of seconds. So it happens really fast. All of a sudden, no more explosion. So gravity takes over. So whereas in a white dwarf, the fusion turns off rather gradually, in a supernova, the fusion just abruptly turns off, and the exterior of the star, all of a sudden, there's no more explosion propping it up, and so it all collapses. So, in a matter of seconds, really rapidly, you have a all of the gravitational potential energy of the star is released. Okay, and what that does is it takes, so you have 100% of the star's um, gravitational potential energy is released, and that gravitational potential energy is given to maybe 10% of the star's mass as kinetic energy. And so there's gigantic explosion of, okay? And in a supernova, a single star becomes as bright as an entire galaxy for a while. So for a couple weeks or a couple months. And so it's an extremely violent event. It destroys the solar system. Everything that's in the solar system gets, roasted. Actually, we believe that it could, if there was a nearby supernova, it could trigger a an extinction event. So if the sun is not going to go supernova, it doesn't have enough mass. But if a nearby star went supernova, it could trigger an extinction event. Now, not in the way that you might think. So what happens is that what we think would happen is that if a star close enough to us went supernova, the radiation from it would change the atmospheric chemistry. So it's not like we would all just drop dead. It would change the atmospheric chemistry, which makes it so that the atmosphere is not as good at blocking ultraviolet light. So basically, we would all, we wouldn't be as protected from our own sun's rays by the atmosphere, because the atmosphere protects us from the sun. And so that would cause extinction. So basically, the sun, it would make the sun, our own sun's light, a lot more harsh, which can cause species. It can sort of destabilize our ecosystem and cause extinction. Not overnight, though. So that's a supernova. Supernovas, if one happened in our own galaxy, it would be bright enough to see during the daytime. So it would be like a second star is visible during the daytime. And at nighttime, if a supernova was in the sky, you would be able to read at night by the light of the supernova. So what's left behind after a supernova, you have two options. If it is a higher mass star, you're going to be left behind with what's called a black hole. Okay? And so a black hole, basically what happens is you have no more fusion happening in the core of the star. And, maybe I'll talk about the other option. So if you're a high mass star, but you're on the lower end of the high mass part of the stellar distribution, you become what's called a neutron star. Okay? So what happens in a neutron star is, again, fusion stops in the core of the star and gravity compresses the star. And gravity compresses the star so much that the electrons get pushed into the protons. Now, what happens when an electron gets pushed into a proton is it becomes a neutron. So the star is made up entirely out of neutrons now. And it's incredibly dense. So basically, it's really hard to push neutrons into each other. So it's held up by the fact that by the strength of neutrons to resist compression. It's called neutron degeneracy pressure. And one of the things I read when I was a kid is that if you were to take a spoonful of neutron star material, it weighs as much as a mountain range. So that's how dense a neutron star is. But if the star has enough mass, then not even the strength, the rigidity of neutrons is enough to prevent the collapse, and it just continues to collapse. And nothing is able to stop the collapse. So it just keeps collapsing, and it collapses to a point called the singularity. And the gravity near the singularity is so strong that not even light can escape. And so where the star was is so dense that not even light can escape, so it just appears black, and you have what's called a black hole. Okay? So yeah. So basically all stars are going to go through the stage of protostar to main sequence to giant phase. But then, depending on its mass, it might end up as either a white dwarf, a neutron star, or a black hole. Okay? So the fate depends on the mass of the initial star. Okay? So the sun is such that it's going to become a white dwarf. Let me talk really briefly, because I'm going a little bit long, but I want to talk briefly about stellar classification. Okay, so we classify stars according this is for main sequence stars. So we classify main sequence stars according to a letter: O, B, A, F, G, K, M. Okay. So the way you can remember the order of this classification is a mnemonic: O, B, A, fine, girl or guy, according to your preference. Kiss me. O, be a fine girl, kiss me. That's the mnemonic to remember it. Now, stars on the O end of the spectrum are high mass stars. On the M end of the spectrum, they're low mass. Okay? Now, because of their high mass, the O-type stars burn hotter. Okay? The low mass stars are cooler. They're still hot. You know, you're still going to get roasted by an M-type star. It's just not as hot. Now, as we learned, the color, temperature determines color. So O-type stars tend to be blue, which is and then M-type stars tend to be red. Now, it's not like a rainbow. It's not like it goes from, from red all the way through Roy G. Biv. It's more like blue to white to yellow to orange to red. Okay? So that's kind of where it is. So there's no green stars. There's no purple stars. It goes along there. Now, the life of a star varies greatly depending on its classification. So O-type stars might only live 10 million years. Okay? It might even be less than that, but it's not long at all on the time scale of the universe. Whereas red stars, M-type stars, could live trillions of years. Okay? Now, where does the sun lie on this spectrum? Our own sun. Our sun is a G-type star. So that's why it has its yellowish white color. And actually, the sun appears yellow because of the atmosphere. If you were to be out in outer space, it's more of a whitish color. Um, as far as we know, um, and when I say the life of a star, I mean what is it? How long does it live before it turns into one of these three? Okay, so how long is it going to take to become a black hole or a neutron star or a white dwarf? These are actually sometimes called stellar remnants. They're what's left over after the star is done burning. Um, so the sun is going to be about 10 billion years in its life cycle. So it's about halfway through its main sequence life. Um, all right. Because we believe the Earth is roughly 4 billion years old. And then towards the end of that, the protostar phase and the giant phase are very short compared to the main sequence. So basically what will happen is after another 6 billion years, the sun's going to start to get a lot bigger and turn into the giant phase. And we've got to either move out to a further point in the solar system, or we've got to move to a different star. If we haven't destroyed ourselves already, we will have to move. Maybe we'll be powerful enough to move the Earth, change its orbit. I don't know. So yeah, this is the. Oh, and of course, also O-type stars are bigger, and M-type stars are smaller. Sometimes Jupiter is called a failed star because Jupiter is somewhat close to the minimum mass required to become a star. So Jupiter doesn't have any fusion happening in its core. But I believe if the mass of Jupiter was something like 10 times as large, it would actually have enough mass to ignite fusion in its core. So, an M-type star is something fairly close to like Jupiter in size. All right, so that's my lesson for today. Let me just briefly repeat my news. There's going to be no class tomorrow. There's going to be no daily item today. And next week will be our last week of lessons. And there's going to be no quiz for this week. But next week there will be a quiz on astrophysics. All right? So have a wonderful afternoon and a great weekend. Bye now. I hope you enjoyed.